Okay, so I'm live now. Think we're going good then. So thank you for the few of you that came in today. I'm Brendan. I'm joined by Rashid. We're from MathSoc. We're going to be walking through just some revision slides for Math 2601 and a bit of Math 2501. Of course, this is mainly what most of the slides are going to cover, a bit of content that's in Maths 2601 that's not actually in Math 2501. I'll try my best to point out which is and which isn't, so you can have a bit of a snooze while going through the Math 2601 slides. But let's get started then. So I'll be walking through the first three topics. So today we'll be going through, I believe, 5 topics. I'll be going through the first three. The first one being group theory and fields, which is something that's not covered, I believe, to really any extent in 2501. But then the next two that I'll be going through are vector spaces and linear transformations, which have a decent amount of overlap with 2501. Okay. So if you have any questions at any point or want some elaboration, feel free to pop your hand up. I'll try to just move this so I can see maybe any potential hands that pop up a bit better. Otherwise, I'll just go through the slides and try to give my intuition in all this. So we'll get started on groups and fields. So this topic, hopefully you remember some of it from the earlier stages of the course, but I guess looking back now, for those of you that do 2601, hopefully as we go through this again right now, you hopefully see some parallels between the study of groups and then later on the study of vector spaces that we looked on later in the course, and also with linear transformations. There's kind of the similarity between linear transformations for vector spaces and then homeomorphisms for groups. So the groups kind of motivate the way that we look at vector spaces, and we'll see that in a second. Let's just get down to the definition. Something I should say, I don't know if it's true as well for 2501, but for 2601, unlike many of the other math courses some of you may be doing this term and have probably done previous terms, you're not allowed to bring a formula sheet into the exam, which is quite annoying. So you're not allowed to write up your 2-page microscopic font formula sheets. So you actually have to remember a lot of the definitions and a lot of the main formulas and theorems that you'll need. So I'll try to walk through the main types of definitions we need to know. I think mainly the intuition is the most important thing. So starting off with one of the most important definitions, we're looking at what a group is. So a group is just a set together with a little binary operation, which we might denote as this little star. And there's 4, or we would say group axioms that the group has to satisfy the set itself together with that operation. The first one is closure. So we're saying if we take 2 objects from the group, 2 elements from the group, and we do that operation on them, then we're still within the group. So we're kind of staying within the set, which is what we would ideally like. So that we can kind of keep doing the operation once we've already done it to get another element. The next axiom is associativity. So in terms of associativity, that's something you see very, very often with, say, typical groups, such as the group of real numbers are under addition, or the group of, say, integers real numbers under multiplication, or integers under addition, because that's something, say, multiplication, addition, and so forth. Associativity for those operations is kind of elementary. So you learned that from primary school, and now we're talking about it again, but in generality, we need our group to have associativity for it to be nice, in the sense that that's what we want for a group. But that just means that we can really do an operation of 3 in any order. So we can group up the second 2 and multiply that with the first one in terms of the group operation, or we can do it the end. The next 2 are kind of the interesting part of the group. So that's kind of the most important thing to what's the group structure is. So first of all, we have the identity. So the identity is an element such that when we do the operation with that element and another element within our group, it leaves it intact. We would say that on either side of the operation, if we put our identity, which we typically denote as E, to another element A, then it just leaves A just there sitting there. Okay, so that's just popping A out. So an example is with the group of integers under addition, the identity is 0. With the group of multiplication of real numbers under the multiplication operation, then the identity is 1. And then say with the group of invertible matrices under matrix multiplication, the identity is the identity matrix, right? So kind of this identity in terms of a group is a generalization of the 0 or 1 in terms of identities in those types of operations. And likewise, since we have this infrastructure of an identity, we can also define what an inverse is. So inverse is something that, given a specific element, there's going to be unique other elements. Well, we haven't claimed that it's unique yet, but on a future slide, I'll show you why it is unique, or just show you the limit that says it is unique. But there's another element in our set that we need, such that when we multiply with our original element, we just get our identity. So kind of simplifies it in a sort of way, right? So there's kind of the inverse, the opposite of a particular element that can get us back to our starting point of an identity. Okay. The next little last definition we need just for now is the definition of an abelian group. So an abelian group is where this operation is commutative, meaning we can go our A star B is being the same as B star A. So it's not always true that groups are commutative in terms of groups being abelian, because there's examples of non-abelian groups. An example is this one here, the general linear group. So the general linear group is the group of all invertible n by n matrices of size n by m, and we're saying that if that matrix is invertible, then we're saying it's inside of this general linear group, and the operation here is matrix multiplication. So hopefully you guys remember that with matrix multiplication, it's not necessarily true that AB is equal to BA all the time. Maybe cases where it is, but in general, it's not. And so that's an example of a non-abelian group. And this is also a very important example because we're, of course, studying matrices and linear transformations in this course a lot. This is an important group that we care about, okay? Other examples of groups that are abelian are, say, the more classical ones, such as I keep mentioning, is the group of integers under addition and group of real numbers under multiplication. Okay? And there's some other examples here with groups. If you remember a bit more of our study of groups from 2601, then you remember there's this close relationship between symmetries of abstracted mathematical objects and groups. So we're talking about, say, with the cyclic group, that's the group of all rotational symmetries of an n. Okay? You can look at similar things with the dihedral and symmetric groups in terms of geometric interpretations of symmetry and rotations, isometries, and permutations. Okay, so as promised, there are a few properties that we need straight from our group axioms. These follow for any group. That first of all, we have a unique identity. So the identity is going to be the same. Well, it's not the same, but we can't have multiple identities. We just have to have the one. And likewise, we also have to have a unique inverse for every single element. Okay, so we can't have different inverses. So we need exactly one, such that if we multiply it on each side, we get back our identity. Next is that with the inverse of the inverse is just the element itself. So kind of mirroring that idea of when we're considering the operation, we have closure under the operation, so we're staying within the set. This kind of mirroring that in the sense that when we take the inverse, we get back our original. The next one is a property that is kind of mirrored throughout this course a lot. So we're saying that when we take the inverse of the product, I really should have A star B here. We're taking A star B inverse. That's B inverse star A inverse. So what this is saying is that the best example I've ever heard is that if you want to invert the process of saying going into a lecture room and then logging in, to invert that, you first have to log out. So that's doing the second step first, and then you have to leave the room, right? So you have to do kind of like a stack. You're stacking up. So you have to do the most immediate one you just did first, and then A. And this is kind of mirrored in a few things we'll see in this course. First of all, say with the transpose of AB in terms of matrices, that's going to be B transpose A transpose. Likewise, with, say, the inverse matrix of AB, if A and B are invertible, then this is B inverse A inverse. Okay. And then finally, our last little lemma here is that we have cancellation in the group. So if we have two products equal to each other, so we have BA equals to CA, then we can cancel out A with its inverse. So to say B equals to C. All right, so we have a little question here that we now want to work through. So we have, we're given a group G and we want to show a little identity regarding the product of all elements within our group that aren't the identity in this kind of specific order. Well, it's a really arbitrary order because this ordering is a bit arbitrary as well. So what we want to show is that G squared is equal to exactly the identity. So let's go and just write that up starting. So starting off by definition, we can write this out like this. Dots. So this is what G squared actually is, because we're just copying G again here. Then we kind of want to look at what the question gives us. So it tells us that this group is abelian, and finite, I guess, but the main point is that it is abelian, and that's what we want to use. So if you're doing this question like formally in the exam, you'd have to like write on the side maybe we're going to use that the group it's abelian, and that we're going to use also associativity, so forth. Since I'm talking to you, I'll just say that and be a bit lazy and just write out the key points here. So what I'm going to say is that we can look like one element at a time. So if we have a look at, say, A1 on this side, then since we know this group is abelian, what we can kind of do is just look at kind of one of the elements here. So I'm going to make the claim that one of the elements on this side is going to be A inverse. So I'm going to write it and group up A1 with A inverse like this, because what I'm going to say is that A inverse has to be on this side because we have that, well, I guess from the uniqueness of inverses that the inverse of E has to be itself. So all these other elements, A1 through to AN, they have to have, well, an inverse exists for each of them, and they have to be at least one of the elements here, right? So we're saying that we're grabbing whichever one it is. It could be any of these N, well, exactly one of them that is the inverse of A, and we're putting it next to A1. And you can hopefully see kind of the inductive reasoning as to what we're going to do next. We're going to just keep writing this out as then A2 times A2 inverse, dot, 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 and we're eventually going to get to AN minus 1. So kind of inductive reasoning there by I'm using the fact that it's an abelian group to kind of switch the order around. It's shifting like forward a bunch of times, okay? So hopefully you can see how that's working. Then this just becomes E star B plus E star E a bunch of times. So it's actually ends up being E to the N, where in a group you would define E to the N as just, well, really doing the operation on your element N times, and it turns out that, of course, since we have the identity, this is just E. So that's what we wanted to show right here. Okay. And that's what I have written up here. And yeah, so permutation, the uniqueness of inverses. All right, so now we want to look at the idea of a subgroup. So we'll see this idea of a sub something many times in this course. So we'll see the idea of a subfield and then a sub space of a vector space. So we're going to see how they're very similar to each other. First of all, start off with this one. So we are given the idea of a group here, and we want to talk about how we can kind of get a subset of that group, what it means to have a smaller sample of that group. So what we would mean by that is that we have a subgroup H of a group G. When we have a subset in terms of G itself, we have a subset of G. H is a subset of G. We would write that like this. And it also turns out that H with the same operation is itself a group. Okay, and then we denote it like this to say H is a subgroup of G. All right, so that's our little definition. Now we need a little help in determining whether or not a type of criteria to determine whether or not we do have a subgroup in some circumstances or others. So what we can say is, given a subset H of G, and it's probably very easy to determine whether or not we do have a subset, we can determine whether or not it is a subgroup by checking if it satisfies these three conditions. And if it does, then it is a subgroup. So the reason why we need all three of these is because I don't think I explicitly mentioned this, but the first one is saying that H is non-empty because I didn't explicitly mention this, but a group has to be non-empty. So I guess that's just making sure that first type of prerequisite axiom is being held up. Then the next two satisfy another two group axiom. So this one here is saying that we have closure under the operation. So we're not going to get any elements that go outside of H into kind of the part of G that H is not covering. And then we're also saying the same thing with the inverse is also going to be in H. Okay. So in terms of the other group axioms, if you remember from a few slides ago, we talked about there is additionally the identity that needs to be in the group. And hopefully you can see, well, kind of by combining all three, we can get that the identity has to be in this H group. The reason being is because what we can say is, well, H is non-empty, so there has to be some sort of element, A in H. In particular, that element A also has to have its inverse in H, so we have to have at least A and A inverse. And they may not be distinct. For instance, the inverse of the identity is itself, so it could be just one element, but at least one element. But what we can do is just multiply A by A inverse, and due to this property, that has to be the identity by definition, and then that means that the identity has to be in H. So we know that the last group axiom is held up. So we just have this more or less efficient criteria to work out whether or not we do have a subgroup. So that's similar to the subspace theorem that we'll look at with vector spaces. And now I'll just show you as well a more efficient way to write this criteria, just real quick. So Sean didn't, Sean, the 2601 lecturer, didn't explicitly use this criteria, or didn't explicitly give this criteria in the lecture slides, but he did use it in, I believe, in one example. So what this is saying is similar to how instead of with grouping a subspace is a subspace, instead of just showing that we have closure under addition and closure under scalar multiplication separately, what we can instead do is just more efficiently show that for any u plus any u and v in our subspace and any lambda being a scalar, then this is also in our subspace. So this is what we're kind of doing here. We're combining these two into one. So we're saying that, oh, first of all, it has to be non-empty. So that's satisfying the first criteria. Then we're saying that we're kind of replicating this by saying the multiplication here and then also the inverse. Because we can say, well, if you do the same reasoning that we did before, you can kind of work out that it has to contain the identity element, and then you can also work out it has to contain inverses if you set, say, A to be that identity element, and also, I guess, if you set B to be the inverse of the inverse, then it also works out that way, okay? So it turns out that this works out nicely here. All right, so now we have this infrastructure of a group. We can use this to define a field now. So if you remember from Math 1241, you probably remember that big ugly definition of a field with like 9 axioms to define it. So here we're doing that a bit more efficiently and a bit more nicely to define a field. So we're saying that a field is a set F together with 2 binary operations, such that with the first operation, which we would call addition, that forms an abelian group, so the additive group. And then if we take away the identity element from this additive group, which we would denote as 0, then we're left with the rest of the elements in F, we're left with a abelian group of multiplication. Okay, so this kind of combines a whole 8 axioms into one, so it's quite nice to write it like this. And then finally, the last condition is that we need distributivity in our field. So just keep in mind that we don't want to forget about that one. And examples of some fields are, of course, you might have seen the rational numbers is an example of a field, or the real numbers an example of a field. There's also finite fields. We don't look at those too much, but they typically involve some sort of the operations often being involving modular arithmetic. So that's when we take the remainder after we divide by a number. For those of you that remember 1081. So that's what we would call the Galois field. It's isomorphic to the Galois field. We'll define isomorphisms a bit later, but we'll say the Galois field has a prime number to the power of k many elements, because that's kind of how it works out, because modular arithmetic with prime numbers is just more convenient and turns out to be necessary and sufficient in terms of prime power, specifically to define a field. And really, if you want to look further into it, it's really polynomials in terms of modular arithmetic. That's a bit outside the scope here. So some basic field properties is that, first of all, we have that cancellation again, because we still have the inverses. we have that multiplication by 0 is still 0. We can bring out the negatives from a product. So typical thing, like things you would just think would work, they turn out to be able to work, but you might want to review some of the proofs of these from like your first principles, because much of the questions from this first topic would be proof related. The next property that we have is sometimes called the no non-zero divisors property, where if we have a product equal to 0, then one of the elements in the product has to be 0. Okay, so like with subgroups, we can also define what a subfield is. So that's when we have a subset of our field, and then we're saying that that is itself a field. So hopefully that's following from what we talked about with a subgroup. And then we can also define what kind of field extensions, where instead of a subfield, we have a superfield. If you kind of, that's not precise enough to say, it's not really well defined, but it's that kind of idea. So we're talking about, an example is, say, if we have the set of rational numbers and we make a field off that with addition and multiplication, what we can also define is a field that is the set of rational numbers, well, the smallest field containing the set of rational numbers and a specific element, say alpha, that's not in the rational numbers, so like this. So any element in C that's not in the rational numbers. So an example is, say, the classic one, Q, say root 2, which is the field with addition and multiplication as usual, but we write it as, say, A plus B root 2, where A, B are in the rational numbers of this. Okay? So that's another example. Okay, so with subfields, we also have a subfield lemma that tells us when we have a subfield from a specific subset of of F. So it's really the same as what we saw before. So we're saying that neither of our two groups are empty in terms of the additive group and the multiplicative group that we need for a field. So that's what these two are saying, because remember, for the 0, this second part here, we're saying that we exclude 0 from the multiplicative group, so we need at least another element there. These ones, respectively, are saying that we have closure under the operation for the multiplicative and additive group. And then finally, we have inverses exist for each of them as well. And we don't have to worry really about proving that distributivity is present within our group, because that's kind of inherited from our original group. And that's kind of something that follows is what follows, say, the subgroup lemma, where we say that associativity is inherited from the original group, and you can kind of say that many times. Okay, so we're given now an example of a question where we're given a set, and we're told that we're going to be defining addition and multiplication as per modulo 12. So what we want to show is that this set F is going to be a field. So we want to show that the axioms hold, or otherwise we can show that we can form that additive and multiplicative group, but we are allowed to assume we hold the distributive law. So the main part we want to do is now just show that we can satisfy the additive group requirement and the multiplicative group requirement. So the kind of cleanest way to do this is to set up some operation tables. First of all, like your addition table, then your multiplication table. So you can kind of just line up all your elements and get a look at what all the different types of combinations are. And then you want to kind of reason about whether or not inverses exist and whether or not your identities exist. So let's do that like this. So for those of you a bit rusty on your modular arithmetic, I'll just outline that briefly, explain briefly what that's going to be. So first of all, adding 0 to anything just kind of keeps everything put, but it gets a bit more interesting. Well, this would be 8 because that's 4 plus 4. It gets a bit more interesting when we get to something like this, which is 4 plus 8, which is 12. But since we're trying to do addition modulo 12, that means we're kind of treating 12 as a 0, because we're looking at the sum. When we take a sum, we're looking at its remainder when we divide by 12, and when we divide by 12 of 12, the remainder is 0. Likewise, this side, this would be 12, but the remainder is 0. This would be 16, but when we divide that by 12, the remainder is then 4. Okay, and multiplication, 0 times anything is 0. So we're just taking the remainder. 4 times 4 is 16, so that would then be 4. 4 times 8 is 32. but that would then be 8 if we take the remainder. You can verify that if you like. Likewise, this would be 8. Verify that. And this one would be 4 here, okay? So you can verify the precise details if you want, but by looking at these tables, what we could say, if we exclude, we're going to take a guess and say that this is our additive identity. So we're going to exclude in our multiplicative group this 0 row and column part. So we're just going to look at this being our, those 4, that kind of block representing our, what we would like our multiplicative group here to be. And so we see that every single row and column here is a permutation of the elements. So that means that we do in fact have a group, and you can hopefully see that here, for instance, the multiplicative identity is going to be 4 because 4 times, not multiplicative identity, multiplicative identity is in fact 4, because if we multiply 4 by 4, it remains 4. We multiply 4 by 8, it remains 8, so it's keeping everything intact. And say here as well, the inverse of 8 is going to be itself. Inverse of 4 is going to be itself, so it works out quite nicely like this. And then the additive group, here the same thing, where we have a permutation of each row and columns of those elements. Okay, so you can see a bit more precise details here if you want. That's just basically saying what I was. So you can see how the additive groups and multiplicative groups follow, and then distributivity, well, the question tells us we don't have to worry about that, but you would say it's inherited from how modular arithmetic is set up. Okay. All right. So the next kind of interesting topic we want to look at is this idea of a homeomorphism. So a homeomorphism from one group to another, so group G to group H, is what we would call a structure preserving mapping. So it's something that kind of gives us a bit of information about how much the structure of a group G is replicated in a group H. So the way that we can do that is by looking at specific mappings that we call homeomorphisms, that such that when we take the map of a product in one group, it becomes the product of the maps in another group. And so like this. So that's just the definition here. We have the binary operation star in G and dot in H. So what this homeomorphism kind of says is that since it's kind of preserving that operation, it's saying that kind of where we map to is kind of a replica in a little way of G. Okay, so we'll get a bit more precise idea of that in some, well, I guess now, because what a put in that on this idea of homeomorphism, we can define a group isomorphism, which is what happens when we allow this function phi to be injective and surjective, meaning that it is bijective. So when phi is bijective, that means that what we can say is that, well, every element in G maps to a unique element in H, and every element in H, in fact. So that kind of, we're saying the structure of G is kind of exactly the same as H, because we just really we're going from one side to the other. We're really just doing a relabeling on our elements. So that's what isomorphism really means. We're just, the groups are the same, they're just relabels of each other. Okay, and it turns out that group isomorphism is an equivalence relationship, meaning that you have reflexivity, meaning that if G is isomorphic to itself, you have transitivity, that if G is isomorphic to H and H is isomorphic to some other group K, then G is also isomorphic to K, and you also have that if G is isomorphic to H, then H is isomorphic to G. In particular, because from this lemma, that the inverse of if an inverse exists for an isomorphism, meaning that we have in particular, if we have an isomorphism, then the inverse exists, and that inverse is also an isomorphism. Okay, because of reflexivity. In particular, some lemmas we have is that kind of stemming from that idea that the structure in G is replicated in H for a group, that we have that the identity in G, the map of that under any homeomorphism, has to be the identity in H, and also the map of the inverses in G have to be the inverses in H. That's what this second point is saying here, essentially, because we're kind of replicating that structure. Okay, so this is where it gets a bit technical in terms of this kind of loose intuition behind replicating the structure of a group. So what we can define as the kernel of a group is the way I like to think about it is the elements of G that can't really be replicated in H. So the only kind of choice we have is to just send them to the identity. So that's what this kind of represents. In linear maps, the kernel is everything that maps to the zero vector. So kind of similar in terms of linear transformations. And then the image, however, is kind of everything in G that can be replicated within H. So it's what we can send to other elements in H that can be represented. So the image is going to be a subset of H, so it's kind of representing, looking at what parts of G can be represented in H, and whereas there may be other parts of H that can't be represented in G, okay? So hopefully that makes a bit of sense, but you can have a look at the precise definitions there. Okay, so we have a lemma here that says that the kernel of G is a subgroup, and likewise is the image, which is quite convenient for us, so that when we work with it, it's pretty nice. And then we have another little lemma that tells us that a homeomorphism is injective, meaning that it goes and takes distinct elements from G and gives them distinct elements in H, meaning that no two distinct elements map to the same element in H. We say that it's injective, meaning what I just explained, if and only if the kernel is just the identity element. So from what I said before, the kernel is at least the identity element by this definition. Lemma and from the definition. But if it is just the identity element, then it turns out that our function is also injective, right? So that's hopefully useful for us when we're trying to look at when a homeomorphism might be an isomorphism. Okay. All right. So now we just have a little, I think, question to wrap up this topic of group theory. So what we have here is a little group that we're saying is a subgroup of the general linear group of invertible 3x3 matrices that have this particular shape where we have lower triangular matrix, a lower triangular matrix of ones on the diagonal, and then we have alpha, beta, gamma filling up these elements. It can be really anything from R, we're saying. And we're defining this set for now, H. We don't know if it's a subgroup just yet. We're saying that H is the set of matrices, specifically in G, such that they commute with every other element in G. That's what this really is saying here, as in we can switch the order of multiplication of the elements X and A. So what we want to first do is show that if X is an element of H, that occurs if and only if X takes this particular form. Okay, so I think for both 2601 and 2501, I need to also remind myself is that whenever we see a question like this that involves an if and only if type proof, you want to make sure you prove both directions. So don't forget to look at both of them. So what we can look at here is we can split it into two different cases. So our first case will be looking at proving if we take this type of element X with this type of structure, that we can say that this is in fact in H. So if we take this element X, we want to show that, for some scalar, we want to show that for X, we want to show that XA is equal to AX. And so let's have a look at how we can just briefly do that. So let's try to, if we take some arbitrary A, we want to show that 1 alpha beta 0 1 gamma 0 0 1 times this 1 0 lambda 0 1 0 1. We can have a look at briefly what this is. It's going to be 1 here, alpha beta plus lambda. This will be 0 1 gamma 0 0 1, and it turns out that that's also what we switch the order. You can verify this in your head if you would like, just briefly. If we switch the order, that's what this would be. 1 alpha beta. Okay, you can verify that if you would like. 0 0 1. So that means that we have that this X in this particular form is within this subgroup H. And now we also want to show that if we have an element in X, then it has this particular, or in H, it has this particular form. So we want to show basically if the other directions, the kind of other direction, if and only if we want to show that if we take some sort of element, if we're saying x is, so it has to be of the form 1, say mu, just want to check what type of notation I use, mu lambda v. So if it has this type of form, just replicating this, but we're changing the letters alpha, beta, gamma, 0, 1, 1. Then we want to show, we want to pull out from the equations. We want to have a look at what the equations would be, because we want to make sure that this is equal to 0 if we take it for any arbitrary element A in G. We want to show that that is equal to 0. So I did the computation down here. You can see with this type of construction in this reverse direction that it turns out to look like this, where we have everything 0 except for this little element down here, and for it to be exactly equal to the 0 matrix, we need this to be 0 for all of our alphas and our gammas, because we need it to be true for all A, as in we want commutativity with all A. So in particular, we need that can only be true if mu and v are equal to 0. In other words, we're just left with this lambda here as we would want, okay? So moving on a little bit, that means that we can think about how we can prove that H is in fact a subgroup of G. So we're looking at now that H is the group of elements within G that look like this. So we have, I guess, associativity immediately being inherited, because our operation here is multiplication of matrices. From there, we also want to verify, I guess, by the subgroup lemma, we can just be more efficient here, that we want closure under our matrix multiplication operation here. So we want to show that if we take two distinct elements like this, then we remain within the group. And we also want to show that the E inverses also remain in the group. So I'll just briefly walk you through what I had written up here in regards to how we do that. So basically, if we take some X and Y in the group, where we're saying Y is now, say, not in the group yet, but now set H, Y would be some, I'm choosing a bit cheekily negative mu, for the reason that when we multiply X and Y like this, it turns out we get kind of nicely that what it turns out to be is the diagonal stays put, and we just get that we get the sum of lambda and this negative mu here. So what that is saying is that the reason why I kind of chose negative mu here, because I was trying to use that kind of more optimized version of the subgroup lemma, where you can show instead that A star B inverse is within your subgroup to show that it is a subgroup, and then just say that it's non-empty would be the only other thing you need to do. So hopefully you can see that this element Y would be the inverse of, say, like the element with, instead of negative mu, instead of mu here. So that's the inverse, right? Inverse of 1, 0, actually mu, 0, 1, 0. And it might be a good idea for a question like this to introduce some good notation, like say subscripts or something. But then you can see hopefully that since this is just the same kind of thing as what we had before with the lambda here, and everything else is either ones or zeros in this specific form, this is just another type of number, lambda minus nu, so it's also remaining within our subgroup H. So we have, from the kind of optimized version of the subgroup lemma, it follows that this is in fact a subgroup, this set H. Okay, so you could have done those individually, as in you could have just looked at the product of X and Y, and then also shown that the inverse of any Y is also in the subgroup, but this is another way of doing it. Okay, so moving on, now we just want to look at this last part, so we're using this idea of isomorphism now. So we want to show that, or we want to have a look at this isomorphism that we're trying to define, that is saying that if we take an element X that's characterized by, well, X was 1, 0, lambda here, we're just pulling out the lambda, and we're saying that that is what we're mapping to. So we're trying to show that this subgroup H is really just the same as the additive group of real numbers. Kind of the reason why is because we saw when we multiplied two matrices, we just got the sum of the two elements down the bottom left. So the way that you can do with this is just by showing, say, if we have some X characterized by lambda and some X characterized by some mu, that phi of x lambda star or dot, in this case, because matrix multiplication. This would in fact be lambda plus mu by that multiplication we just kind of looked at previously. So that shows that it is a homeomorphism. For showing that it is an isomorphism, you don't have to do too much work. What you could just briefly say is that because if you want to, you can get any lambda you want by just making the appropriate lambda here. And you can also say it's injective in terms of it being one-to-one, because for any distinct elements down the bottom left, you get distinct outputs of lambda and mu. And you can also argue that, I guess, in a slightly different way, that there also exists the inverse by if you have some sort of lambda, then you place the lambda down in the bottom left of the matrix, and that's what you're saying your matrix X is. Okay. So yeah, that's basically what I said here. All right. So now on to vector spaces. So I'll try to not spend too much time here because this is mostly revision from also Math 1241, but we'll go over the main ideas here. So like how we define fields as, or by taking the type of group structure we talked about, we can define a field as, well, you can look at as well, if you've only done 2501, those giant list of vector space axioms, so you can also still use those, but if you've done 2601, you can add in the fact that 5 of those axioms kind of follow if you say that your vector space set V is an abelian group with addition. Okay. So you have 2 operations for your vector space, addition and scalar multiplication, where the scalar multiplication follows these types of axioms, whereas addition follows quite nice set of group type axioms. Okay. So there's some examples you can have a look at. So throughout this course, you probably looked at some types of function spaces where you're looking at addition being element-wise of the evaluation of the function at a particular value, and scalar multiplication being element-wise stretching of that particular value. You can also define polynomials, where you're just adding the polynomials together and multiplying together. Specifically, you can define the set of all, say, polynomials over a specific field, and you can also define all polynomials of a specific degree. Specifically, you can define Pn, if I say the real numbers, that's the polynomials of degree up until n over the real numbers. So hopefully you've seen those a lot. So some basic lemmas you may have in a vector space is that scalar multiplication by 0 just gives 0. Scalar multiplication by negatives gives negatives. And you also have that kind of same idea of the no non-zero divisors, where if you have a product equals 0 in terms of scalar multiplication, then either the scalar is 0 or the factor itself is 0, in terms of this 0 being the additive identity of that group in our vector space, the additive group. Okay. And we also have that kind of cancellation idea where we have non-zero scalars. Okay, from that type of field idea, because we're taking scalar multiplication over a field where we had cancellation. So the next, likewise, following off from subgroups and subfields, now we have the definition of a vector subspace. So we're saying that that is a subset of the set V in our vector space, where that subset is also a vector space together with the same operations. And as I spoke about before, we have this very efficient way that we can use to determine whether or not we have a subspace by saying that if U and V are elements of our subset and lambda is our element in our field, then we need U plus lambda V to be in our subset as well, to make sure that we have the closure under scalar multiplication, addition, and then existence of negatives and so forth within our subfield that satisfies everything we actually need. It's quite nice how that works out. Okay. So the next kind of definition we need is a span, and to motivate that we need, or to define that well, we need to define what a linear combination is properly. So a linear combination is where we have a set of vectors and we're looking at the sum of all those vectors multiplied by some respective scalars. Okay. So using that, we can define a span to be the set of all linear combinations of a particular set of vectors. And we're saying that well, there's some things we can say is special about a span. So if the span is the vector space itself, then we would say that it's a spanning set. In particular, we can also say that any span is also a vector subspace of our space V. So we would write that like this. Been using this notation a bit Just to clarify this, less than or equal to means subspace of, or in groups it meant subgroup of. And in particular, when this is an inequality, so when it's true that span of S is equal to V, then we're saying S is a spanning set. And just be a bit wary that we define an empty sum to be 0, such that for the empty set, that's also a subspace, being the trivial 0 subspace. Okay. All right, so with linear independence now, we can define that. So given a set S, we can define another property that's pretty much just as important as span, which is linear independence. So we say that a set is linear independent if every single linear combination of elements in that set, when we set that linear combination to be equal to 0, there's only one trivial solution where we just set all the scalars to be equal to 0. Otherwise, if that's not true, if they're not linearly independent, we say that there's a linear dependence. We say that the set is linear dependent if there's some sort of non-trivial solution, because that would mean that at least one of the vectors is dependent on the others, as in can be written as a linear combination of the others by rearranging this type of equation. Okay, so why do we care about linear independence and spanning sets? Is because it allows us to, well, first of all, just some lemmas, and then it'll allow us to define a basis. First of all, is that when we have a set of dependent vectors, then we can remove one of those vectors to get the same span, because we said that one of the linear combinations of one of the vectors, or linear combination, one of the vectors was a linear combination of the others, so we can just remove that one and we get no loss of information. Likewise, if we have a vector within the span, then that means that we can form a linear dependence. So combining that with S, we get a linear dependence. And these kind of facts and lemmas about linear independence and dependence kind of motivate this definition of a basis. So a basis is quite a nice set within a vector space. So there's not necessarily a unique basis, but there are certain nice ones that can exist for, say, polynomials. That's the basis of, say, 1, then x squared, you might have seen before. And then we also have the ideas of, say, standard bases in typical vector spaces, like I hat, j hat, k hat. So here we're looking at a basis. So what a basis is a set of vectors such that it is both spanning. So that's what the second one here is saying. It's a spanning set, and it's also linearly independent. And we get that this basis type idea is strong enough such that every single type of basis we could construct has to have the same size, given that we have they are finite, that is. So otherwise we would have what's called an infinite dimensional vector space, which we don't typically look at really to any degree in this course. But we would say that the dimension is the size of any really basis, because they're all the same size. But of course they could contain different types of elements. Okay, so what we can say as well, which might motivate some type of constructions you might be asked on, is that if we have a spanning set, then we can remove some vectors to get a basis. Likewise, if we have an independent set, then we can extend that independent set to also get a basis here. Okay, so now we want to look at, in terms of this basis, what it means to talk about representing vectors in terms of those bases. So we will look at the idea that if we have a basis, then we can write any single vector uniquely as a linear combination of elements within that basis. So we would say that with basis here, that any element phi within our vector space can be written, be expressed really, and that's this idea of a coordinate, be expressed as n different scalars. So n different scalars. The reason why that this works is because the fact that the basis is a spanning set, means that there is at least one solution, lambda 1 through lambda n, for which this is possible. And the fact that it is linearly independent means that it's exactly unique. Okay, so that gives us the idea of a coordinate vector with a special type of notation with the b down the bottom with these square brackets to denote this type of column vector. We have lambda 1 through lambda n here to express our vector in terms with respect to our basis b. Okay, so that's what WIT means with respect to. Okay. And now we'll see how that's useful in the next topic, which is linear transformations. For now, we just have, I believe this is just as well 2601 exclusively, this type of content. We can look at the types of things we can do with different types of vector subspaces, where we can think about what happens if we try to combine them or kind of intersect them. So it turns out if we do take the intersection of two different vector spaces, that it's quite nice that that also turns out to be a vector space, subspace that is. Whereas in general, the union isn't necessarily, because for instance, if you have one vector space which represents geometrically a line and another vector space that represents a different line, taking the union of all those elements gives kind of cross type shape, which is not a vector space. So what we need instead to kind of express this idea of combining two vector spaces together, kind of the same type of thing we would want with the union, but we can't exactly do that. We have to instead do what's called the subset sum, where we take all the kind of pairwise additions of every element in S and every element in T, so adding together all the different combinations of elements within our two vector spaces, and it does turn out that this subspace sum of S and T is good enough such that it is also a vector space. So for instance, like there's that example earlier with two lines, I should write it maybe this two lines, the vector space sum would be the plane formed by those kind of two lines, or parallel to those two lines. Okay, and let's look at an example now regarding this. So we now have we're given some subspaces X, Y, and Z, and we're given these kind of a bit ugly expressions here. And we want to have a look at proving that, well, since we kind of know from the previous lemmas and definitions that both sides are actually vector spaces, we want to show that this side is a subspace of this one. Okay, and the way we're going to do that is kind of by using definitions a bit constructively. So what we would say is we use that inclusion type idea where we're saying if X is in the left-hand side, then we want to show it's also in the right-hand side. So if it's in the left-hand side, we can say that since it's the sum of X and Y plus Z, then it has to be equal to some sort of element W plus some sort of small element Z, such that W is in both X and Y. So W is in X, W is in Y, because we're saying that it's in the intersection of X and Y. So that's the part of the sum we talked about earlier. That's from the X and Y part, whereas the other part would be from the Z. So we're saying that this little Z is in big Z. Okay, so like this. And in particular, what that means, for instance, is that that means that since W is in X and Z is in big Z, in particular, that means that, of course, X would be in the sum of those two has to be in X plus Z, right? Like kind of definition. And likewise, you can obviously see that X would have to also be in Y plus Z. So that means that it's in the intersection of these two vector spaces. So that has to be, well, that is what this right-hand side. So X is also in X plus Z intersected with Y plus Z. And then you could kind of say at the end there that since X was arbitrary, that we have that every single element in the left-hand side is also an element of the right-hand side, okay? So I might leave it as an exercise from there for you guys to try and think about part B, which is trying to ask about when this isn't, when it's not a inequality, as in when there is cases where the subspace here is not exactly the same as the subspace here, as in, I think an example you could use is, say, X is the span of, say, 1, 0, and then Y is the span of 0, 1. And we'll just briefly, well, maybe Z is the span of, say, 1, 1. Hopefully you can see with this type of example, you might want to think through the details and see if this one does work. But you should be able to see that X and Y here is empty. And then if you add that to Z, that's exactly, well, a one-dimensional type vector space, being everything parallel to the 1, 1 vector. Whereas you should see that this side is two-dimensional, if I'm correct. Yeah, it should be two-dimensional because each of these believe should be plain. Or actually, sorry, each of these should be R2 itself. Yeah, so the intersection should also be R2, so they should be both two-dimensional. So you can look through the details of that later if you want, because remember this will be uploaded on YouTube. And there's this other type of example that I will skip for the interest of time. So this one, you can also look at the same type of idea. Remember, as I said before, don't forget to do the if and only if try proof. So we want to show that this left-hand side is a subset of the right-hand side, and conversely, you want to show that the right-hand side is a subset of the left-hand side. Okay, so moving on. So we have a little lemma now, which relates the dimensions of this vector sum, that subspace of vector sum of S and T, to the dimensions of S, T, and their intersection. So this kind of mirroring that inclusion-exclusion principle with sets you might have seen in Math 1081, or within as well, perhaps Math 1B, a little bit from probability. So it's that same kind of idea where we're kind of taking everything in S and T in terms of the dimensions and subtracting off kind of the overlap in terms of the information that the kind of bases betray. So that's kind of motivating what one might do with improving that identity. So what we would say then is that if it turns out that this term is just zero, as in we just have directly that the dimension of the vector space sum is S, the dimension of S plus the dimension of T, as in other words, if the intersection is just exactly the zero vector, so it has dimension zero, then we say that the sum is direct. So that's saying that S and T are kind of very disjoint in terms of the information they convey about vectors, so that they kind of have no overlaps, they have no non-trivial intersections. So that's what we would say is the direct sum. Again, this is 2601 exclusive, I believe, and we denote it with a little looks like this is a circle through it, okay? Instead of just the typical plus. So it's that very special type of sum. What we're allowed to do with a direct sum like this is we're allowed to, what permits us to express every single element within our vector space uniquely as the sum of one element in S and one element in T, okay? So that's quite nice for us because it's saying that, well, the information or the expression of every element within V is can be broken down into something that can be expressed in S and something that can be expressed in P. All right. All right, so moving on a little bit, we can look at this idea of a complementary subspace, which is if you have, say, some sort of subspace S of a vector space V, we know that we can extend the vectors in S to, well, extend, say, a basis in S to make a whole basis for V. And then we can say what we can do is say, take the elements in that basis that aren't in S already, and that can form some set T, which we would call a complementary subspace. So we're saying that V can be the union of this kind of non-overlapping vector spaces S and T in this way. Okay, and we call that a complementary subspace, which is not necessarily unique. As going back to maybe that example of two lines, if we have one line being S and we're looking at R2 here, we can really choose any non-parallel lines such that S direct sum T would be exactly R2. So that follows for some of you. All right, so moving on, we have a little question now. So this question is, well, kind of chose one that's not really too computational because I wanted to kind of test these types of definitions. So what we have here, similar to what we looked at before with that group question, is we have that with the vector space of 2 by 2 matrices, which is in fact a vector space, we're looking at defining a set W A with some sort of fixed matrix A and V. We're saying that it's the set of other matrices such that they commute with A. Okay. And we're told that this WA is a subspace and that it has dimension either 2 or 4. We don't have to prove that because it's not the point here. We want to show that it is not possible to define matrices A and B such that V equals WA plus WB. Okay. So you might think immediately that that might kind of go against what I was speaking about before, where there always exists that complementary subspace T given some sort of S such that V is the direct sum of S and T. But the reason why that's not going to work here is because we're restricting ourselves to working with only subspaces of this particular form. So if we're restricted in that way, we can't find a specific other matrix such that a complementary subspace can be expressed as specifically one of these WA type subspaces. So what we can first do, given the information that the dimension of WA is either 2 or 4, is that we can kind of look at that this equation we had before, where if we're looking at a direct sum, then it becomes the dimension of S plus T has to be dimension of S plus dimension of T. So here we would need that the dimension of S, or dimension of WA plus the dimension of WB has to be, if we want this to be equal to V, has to be the dimension of V, has to be equal to 4, because that's the dimension of the set of 2 by 2 matrices, because you can have, say, a basis of the 2 by 2 matrices by considering each element as having a 1 in one of the specific 4 cells within your matrix and zeros otherwise. So dimension B. So that means since this number and this number have to be equal to either 2 or 4, hopefully you can see that that means that both dimension of WA and WB have to be equal to 2, so that we need, for this to work, to have, for distinct A and B, two-dimensional vector spaces A and B that have no overlap, such that they give this direct sum. So we need, for this to be a direct sum, we need WA intersected with WB to just be that 0 matrix, whereas this 0 matrix is the matrix here of all zeros. So the way that we can show that this is not true, we can show that's not true, is that we can find one specific element within both. So for instance, what we can say is that since the identity matrix commutes with both A and B, that is A times I is equal to I times A, which is just A, and also B times I is equal to I times B, which is B. We can say that I is in the intersection of WA and WB, which contradicts the fact that we need this to just be the 0 vector. Okay? So this is really harder than most of the types of questions you'll see, but it's a good example to demonstrate the type of intuition, some of the trickier things you'd have to think up for questions like these. Okay. All right, so moving on to the last topic that I'll be covering, we're looking at now linear transformations. So these are quite important and very analogous to those of you that studied isomorphisms in 2601. So what a linear transformation is another example of what I've been saying before, which is a structure preserving mapping from one vector space to another. So we have this little definition here where we're saying a linear transformation is where we can, where it kind of respects the operations of scalar multiplication. So we can pull out the scalars. We can also distribute the sum. Okay, so it's very nice in that way. So it's preserving that additive and scalar multiplicative structure of our vector space in another vector space. So we're going from V to W. Okay, so that's what our linear transformation is. And I've written in this way that kind of resembles it's very similar to what you've seen before with the subspace theorem. So try not to get these two confused, because this can look very similar to what you might want to prove, which was showing that U plus lambda V was in your subspace for every UV in your subspace and every lambda in the field, to show that we had a subspace. This is very different to that, well, slightly different, because we're working with a mapping now, but kind of resembles that same type of idea. Just don't trip these two up. Like, you're talking about either proving that something's linear in this case, whereas before you were proving something is a subspace. Okay, so that's our definition. That's our main definition. And we can talk about what we can look at here. So first of all, another definition is that the set of all linear transformations, we can denote that, and you might see this denoted as with this mathcal L here from V to W. And what that really is just also itself a vector space. So that's saying, well, kind of as I spoke about before, there's very much that similarity between what this looks like with the scalar multiplication and addition here, that kind of relates very much to how we can explore how that resembles the vector space structure, because it can, of course, respect scalar multiplication and addition because it is of itself a function, so you can split it up like that. So you may want to quickly have a look at the lecture slides for a little proof of that if you're a little unsure as to why that is, but hopefully you can see this type of idea here. So some basic lemmas we have about linear maps is kind of similar to the group lemmas we had before, that the image of the zero vector in, well, I should say image of zero vector in V is the zero vector in W. Remember, those might be kind of two distinct objects because one is the zero element within V, the other one's within W. Then we're also saying that the negative within V of a specific element is the negative of the image of V within W through this linear transformation. If our linear transformation is invertible, then we're saying that its inverse is also invertible, because it's kind of like that same type of idea how our group isomorphism, its inverse is also an isomorphism. In terms of composition, then we're saying that's also a linear transformation, because kind of that transitivity type idea similar to that. And then finally, if we define this group where we're saying that the domain and codomain are the same, that is V is equal to W, and we're looking at all the transformations that are invertible, where they have an inverse, then we're saying that that is a group under composition, right? Because we're saying that composition is still linear. We said before that we can define as the inverse here. We know that an inverse exists. That's kind of by definition. And then the identity could just be the identity mapping where we leave everything just the same as before. Okay. So the next kind of definitions we need are the kernel and image of a vector space. So the kernel is the set of everything that maps to the zero vector, and the image is the set of everything that can be mapped out. And those are similar to groups. Those are subspaces of in the kernel has to be a subspace of V, image is a subspace of W specifically. And we can also define the image of a set where we look at everything we get out when we plug in that set. Okay, so the same kind of intuition applies to these two here, as I spoke about before, with the image and kernel of a group, where we're saying that the kernel is everything in kind of this space V that can't really be represented in W, whereas in terms of the image, we're saying that that kind of represents something that can be represented in W. Well, specifically it depends on what our mapping is, because for instance, if we just had the mapping where we map everything to the zero vector, of course that's linear, but we're not really saying much about the similarities between V and W there. And we have this little major theorem here, really. First of all, we can define what the nullity and the rank of a linear transformation is. The rank is going to be the dimension of the image. Nullity is going to be the dimension of the kernel. And the rank nullity theorem says that the dimension of our starting vector space, our vector space V, is going to be equal to the sum of the rank of P and the nullity of P. So we're saying that if we have a higher nullity, then we're mapping more things to zero, so we're getting less out of our mapping. So that means that if we decrease nullity or increase nullity, rank decreases, and vice versa. So it actually is, if you do all the calculations and you look at the proof of this, it does turn out that they're corresponding in that exact way. And you can look at it that way as well. So this is the next key part here in terms of mirroring that idea of group isomorphisms. We can, from this idea of a linear transformation, define what it means for two vector spaces to essentially be the same. So first of all, let's talk about some criteria we can have where our linear transformation is bijective. So if our linear transformation goes from one vector space to another with the same dimension, because we kind of want, if we're going to say two vector spaces are essentially the same, then we kind of, at the very least, need them to have the same size of basis. So we can say that then from there, if the mapping is bijective, that happens if and only if the nullity is zero, and if and only if the rank, that is the dimension of the image, is exactly V. So we're saying that everything corresponds one-to-one from the vector space V, which you can have a look at justifying using that intuition we spoke about earlier in terms of representing everything V, some things in V and W, and also talking about using the rank nullity theorem to relate these two to each other. So from that, we can say that two vector spaces are isomorphic if there is a bijective linear transformation from one to another. Okay. And it turns out that we can say that two vector spaces are isomorphic if exactly the dimensions are equal, because you can show constructively that some sort of vector space isomorphism does exist that satisfies that. Okay. All right, so now in terms of matrices, because matrices are a big part of linear algebra, we'll be talking a bit abstractly until now in terms of linear transformations, but with matrices, it's kind of the same idea, because a matrix is essentially just a representation of a linear map. We'll see a theorem on that in like a couple slides. But for now, what we can say is that for some matrix A, we can define a linear transformation denoted by T of A by a linear transformation kind of induced by multiplying some sort of vector by the matrix A. Okay? And from there, we can define what we can define, not really from there, but we can define the column and row spaces of a matrix A to be the column being the span of all columns in A, which does turn out to be the image of the linear transformation induced by A. Likewise, you can define as well the kernel of a matrix A to be everything such that, the null space of a matrix A to be everything that you that maps to 0 when you multiply them by the matrix A, which also turns out to be the kernel of the linear transformation induced by A. So you kind of have these same analogous definitions of rank and nullity of a matrix in much the same way as a linear map. So let's look at a quick little question here. This is following on from the previous question we did. We looked at the same setup before, but now we're defining a linear transformation with our output kind of being similar to what this is. So we're saying that our output is this difference here for fixed matrix A. We want to show that this mapping T is never an isomorphism. So what we can do to show this is say that, well, since the kernel of T here would exactly be the set of X in V such that AX on, I should write it the other way, XA minus AX is equal to 0. And otherwise you can say that's XA is equal to AX, which is the same as this condition. So we're saying that WA is exactly the kernel of a linear transformation T. And since we know that WA has dimension either 2 or 4, there's another theorem we spoke about earlier, how an isomorphism requires the kernel to be just the 0 vector, as in have the nullity be 0, and we can't have this here because the dimension of the kernel is non-zero. So hopefully you can see how that follows. All right, so this is the main thing I was going to talk about, mainly here. Well, the motivation for it is with this little theorem up here, but the consequence is what I spoke about before, when matrices and linear transformations are the same. Because you remember, this was the vector space of all linear transformations from a vector space V to W, where we're saying that, well, it's implicit that the dimension of V is P. That's right. Oh, the Q. Let me just make sure I don't trim myself up. P by Q matrix here. So it takes in, yeah, dimension of V is Q, and dimension of W is P. So we're saying that if those two conditions hold, then there's an isomorphism given in this way, where we can represent any linear map from one basis to another by a specific matrix, such that what we can do constructively is just slap in each column the representation of the image of each of the basis vectors. So we take, say, basis vector 1 in V, if we're trying to get a expression of the linear transformation from basis B in V to basis C in W, we can slap in the first vector, the image of the first vector expressed in the basis C in the first column, likewise with the second, third, and so on column up until the cube column, because that's the dimension of our basis B, because the dimension of B, or the number of vectors in our basis B. And we're saying that that satisfies this relationship. So what this is kind of saying is the way I interpret this is you kind of cross out the B's and say that it's just leaving up the C, where we're expressing everything in the C basis, because what we're saying is this is our inputs, and so we're inputting in that way, and then cross out like that. And so going back here, just briefly to recap what we might have just missed. Oh, yes, so that's what it's saying there. Dimension V is Q. There's a unique matrix A that satisfies this condition of we're taking the coordinate vector of B multiplied by A to get the transformation with respect to, well, written with respect to C, and that follows by this construction here, which you can look at. And that motivates kind of the change of basis matrix. So the change of basis matrix is this kind of identity matrix. So what we do is just really, we'll follow this idea of slapping in the image of, well, the identity, which is just the matrix itself, but expressed in a different basis. So we're saying this is the identity from basis C to basis B. And so what that does is we're just converting from the coordinate vectors in one basis to another, which allows us to define this kind of nice matrix here, which has the inverse of which is the inverse matrix, which means that really the inverse of any linear transformation as well is just the inverse matrix of that linear transformation. Okay. And from there as well, we can say that the composition of any two linear transformations, well, when it's well defined, so we're going from U to V, and then from V specifically to U, when we're going from S, and then applying T to that, that's the product of the two matrices first, S, and then T with the appropriate bases here. And you can see kind of as well what I mentioned before, where think about the bases in this type of notation, the C's can cancel out there, which I hope you remember, which is the way I try to work with whenever I'm doing the change of basis formula, which is going from a linear transformation in one basis to another. So you can cross out, say, the standard basis here if you want to write like that, and then the standard basis here to express it from basis B to basis C quite nicely using this type of identity matrices, which you just slap in really the column vectors of the basis. Okay. All right, so you can see some examples of those. Hopefully you're familiar with that from the first class test, which was quite a while ago, really, but and we still haven't got our marks back for that for 2601, but we can hope that when we do, we get some nice revision, I guess, the day before the exam of looking through our results there, assuming that we do get them before the exam. So here we can just look at practicing this a little bit. So we want to say, looking at the linear maps, we're looking at some types of linear maps subscripted by X, where we're saying this is taking in polynomials, the vector space of polynomials, the degree at most 1, maybe we should write it as mathcalp, and we're saying that we're mapping that to the evaluation of the polynomial at the specific point X, okay, evaluated in X. We're allowed to assume that this is the set of these maps, Tx, is a vector space, which is specifically going to be the dual space that Rashid might be talking about later, or for those of you from 2601, you might remember, but that's not really necessary to know here. But what we want to show is that we can form a basis of this vector space V star by looking at the transformations where we're evaluating our polynomial at 0 and then evaluating it at 1. So what we want to show is, we want to show that this basis is linearly independent. We also want to show that it is a spanning set. So we really want to show that for any Tx, we can write that as some lambda T0 plus lambda 2T1. Maybe we should write as lambda 0 T0. So lambda 1 T1, just to make the notation a bit cleaner. I guess we don't actually have to explicitly show linear independence and spanning, because you could say that if you show that this is a unique representation, as in there's only one lambda naught and lambda 1, then this is true, that it is both linearly independent and spanning. So I guess we could write it as, well, we need this to be true. If we want this to be true, we need P of X to be equal to lambda naught P of 0 plus lambda 1 P of 1 for any P of X up P, and let's say that's equal to A0 plus A1 T in space of polynomials of degree 1 over R. So we're going to say that but this would be A0 plus X times A1, and this is lambda naught times A0, and this is then lambda 1 times A0 plus A1, just A1. From there, I guess if we said, say A0 is equal to 0 for whatever reason, we would get that, or A lambda 1 is equal to X, well, A1 lambda 1 is equal to A1 like this, which would mean that for this to be true, well, we can set lambda 1 to be equal to X. That's kind of what we need. Okay. I guess if X was 0, then we would need, well, yeah, there's some kind of edge cases there. If X was 0, then it doesn't really matter what A1 is. Or actually, if A1 was 0, rather, it doesn't really matter what X or lambda 1 were. But I'm just going to move on just a little bit. I'll come back to that idea. If we have this, first of all, if lambda 1 is equal to X, I guess we could also set lambda 1 is equal to 0, A1 is equal to 0, which gives us A0 is equal to lambda naught A0 plus lambda 1 A0, which means that, well, 1 is equal to 1 plus lambda, so lambda naught plus lambda 1. And well, we know that lambda 1 is X. Well, that's at least one solution. So lambda naught is equal to 1 minus X. So that that is one solution here, where we're saying that, I guess our coordinate vector for any T of X, well, that's kind of what we're about to say, T of X written in this basis would be, what we're saying, 1 minus X and then X. Okay. Oh, and then specifically for T2 in this basis, we're saying that, because I'm trying to write in this part, just getting a bit ahead of myself, right? The transformation substituted by 2 instead of X would be subbing in -1 and 1 here. If that works out, or -1 and 2 jokes, because we're trying to express 2 here. Believe that would work out. Yeah, it seems good. Now let's go back. So what we basically did here is showed that it was a spanning set. So we showed it's a spanning set. We just want to show as well that it's linearly independent. So I guess it's a bit harder to show that this is the unique solution we would have, because it's a bit more complicated. But what we can show instead is that if, maybe using different letters, if mu naught T naught plus mu naught mu1 T1 is equal to 0, then that means that mu naught and mu1 have to be both equal to 0. So using that kind of notation again, we could say mu naught A naught plus mu naught, or mu1 A naught plus A1 is equal to 0. I guess setting A naught is equal to 0, A1 is equal to 1 means that mu1 is equal to 0. Likewise, we can set A1 equal to 0, A naught is equal to 1 gives mu naught is equal to 0, or similar logic to that. You can verify the precise details, which means that it's not only a spanning set, but also linearly independent, since the only solutions are the trivial mu naught is equal to 0 and mu1 is equal to 0. Okay, and then this would be the representation within that basis of the transformation subscripted by 2. All right. So last little definitions here before we wrap things up on my section is what we call matrix similarity. So similarity inside of matrices, what the kind of algebraic definition is that two matrices A and B are similar if there exists some sort of invertible matrix P such that B is equal to P inverse A times P. And it turns out again that like with what we talked about with isomorphisms, that this is also an equivalence relationship. So it's a nice way of saying how similar, I guess, lack of a better word, how similar two matrices are. And looking at that idea of a change of basis, one can motivate that two matrices are similar if and only if they can represent the same linear map just with respect to different bases in the domain and codomain. So we're saying that matrices A1, A2 are similar if and only if there exist bases B1 and B2 such that A1 represents some sort of linear map, T, with respect to B1 in the domain and B1 in the codomain, whereas A2 is a matrix representation of the linear map with respect to B1 in the domain and B2 in the codomain. Okay, so the same in the domain and the codomain. All right, so then we have this idea of similarity invariance, which is a property shared by all matrices that are similar to each other. So that kind of quantifying what it means for matrices to represent the same linear map. Some properties we need for this are that the determinant is the same, the trace is the same, rank and nullity are the same, because we're kind of talking about the idea of linear transformation. They have to encode the same kind of information in that, whereas the trace and determinant kind of more algebraic that they pop out. You'll see, I believe, Thomas tomorrow, giving the next seminar, is also going to talk about how the Jordan normal form is an absolute similarity invariant, meaning that, well, these ones are necessary conditions for two matrices to be similar, but for sufficiency in terms of they're similar if and only if condition holds, that is the Jordan normal form, which is a core part of the second half of the course, which Thomas will be going through tomorrow. Then I just have one more. We're going to go through this last example, then I'll hand it over to Rashid in just a second. So we're saying here that with two matrices that they're similar if and only if that this kind of eigenvalue type construction, what the thing we do to get our eigenvalues, where we look at A minus lambda I for some, well, in this case, we're not saying that I lambda is a eigenvalue just yet, we're just looking at some sort of scalar. But the way you could do this question is say that, well, and you might want to write it up a bit more formally than I'm about to, but let's say A is, I'm going to just use similar to B. So I'm going to mean this little swig to say similar. If and only if, as in I'm going to draw the double arrow, A is equal to P, B, P inverse, for some invertible P. If and only if, well, all we have to do now is kind of look at A minus lambda I. A minus lambda I is equal to, just add lambda I to both sides, minus lambda I, which means that A minus lambda I. And by the way, I forgot to mention this, I believe similarity invariance is 2601 only as well. P, B, P inverse minus P lambda I, P inverse, just chucking P's and P inverse, because we're working with like or I should really write it like this, lambda P, P inverse, which I can then say, well, this part's just the identity, because we're just writing the identities in a different way. Then what I can do is just factor out the P's, where I get B minus lambda I, because I wanted to kind of bring a P here to get the P and the P inverse to write the matrices in the similar way. And that means that A minus lambda I, and we can bring the P inverse here as well, which means that A minus lambda I is similar to B minus lambda I. Okay, and this is if and only if all of this. Okay, so the last little definition I have now, before I hand it over to Rashid, is that we're saying that a subspace is invariant if doing the operation on every element in that subspace leaves kind of intact in the sense that you don't go outside of that subspace. So you may get, well, you always get that the image of a subspace is also a subspace. So we're saying that the image of the subspace is a subspace of itself, where U is a subspace of V. So you kind of containing yourself just to set V if we're looking at a mapping from V to V. Okay, so that'll be useful when we're talking about the Jordan normal form as well. So I don't actually see Rashid. I see Thomas. You want to take over, Thomas?
Well,
We are up to the next topic, which is inner product spaces. Can you get Thomas? Can you contact Richard?
Well, when you hear it, tell me yours, okay?
I guess while I have you here, then yeah, you can start then, Thomas. Thomas will be taking over tomorrow on the next seminar. I guess since you guys showed up today, you might be interested as well. And you probably already know, for those of you doing 2601, Sean is running a session where he will be going through some final exam questions. So you can have a look at that. That'll be from 11 to 1 tomorrow. And then after that, Thomas will be holding the second half of this revision seminar. I believe Precision Train Geo6 are kind of next door. So I'll hand it over to Rashid now.
Location.
Is it though?
Oh,
Yeah, 06.
oh, okay, that's that.
Yeah.
I'm like,
Besides that, good luck with your exams, everyone. Rashid will take it from here.
Thank you, Brendan.
What?
oh, I see. There we go. It was. What happened to? Yeah, last month, that's for teach one of the repetition.
All right, how's it going, everyone? Let's get started with inner product spaces. So, first things first, let's start with what the inner product is. The inner product is a function between two vectors in a vector space, right? But before we go through the actual properties of it, something to bear in mind, it's a generalization of the dot product that we're familiar with, right? So whenever you see something like this, that's our new notation for the inner product. Just think of it as a kind of generalized dot product, except now where it's generalized to vector spaces that are not just the two that we're familiar with, right? The real and complex vector spaces. So let's look at these properties. If V is a vector space over a field F, then an inner product is a function between two vectors in that vector space and the field, the following properties. So the first property is that it's linear in the second argument, right? So what that means is that this second argument preserves addition and preserves scalar multiplication. It also happens to be that the first argument also preserves addition as a result of the other properties. The next of which is conjugate symmetry, right? So swapping the elements, right, is equivalent to just taking the conjugate of the inner product. And last property, the inner product of a vector with itself always has to be greater than or equal to 0, real, and it can only be 0 if the vector is the 0 vector, right? We can summarize that with the term positive definite. Hopefully you've heard that before. Cool. Yep, and an inner product space is a vector space which comes with a valid inner product function. So here are some examples. The first of which is the most obvious, just the dot product, right, on the real vector space. Another way to notate it is this matrix multiplication notation, which turns out to be useful. And yeah, as you know, it's just the sum of the pairwise products of the terms of the vectors. It's a little bit different for complex vector spaces in that the terms of the vector on the left, we take the conjugate of them before taking the dot product, right? So as an example, the inner product of something like 1 and I and I2, for instance, right, would equal 1 times I plus negative I times 2, right? Does that make sense? So we took the product of this, and the product of the conjugate of I, which is negative I, and 2. And a bit of a more interesting one, we've got an inner product on the vector space of continuous functions on an interval from A to B, right? And in this case, the inner product actually turns out to be an integral. So now that we've generalized the dot product, we can generalize the concept of orthogonality. So this definition should look pretty familiar. We say that two vectors x, y in a vector space V are said to be orthogonal to each other if their inner product is equal to 0. And we can denote this with this perpendicularity symbol like this. Should look pretty familiar. Something similar for the concept of an orthonormal set, right? We say that a set of vectors S is orthonormal if the inner product of a vector from that set with itself is always 1, and the inner product of two different vectors from that set is always 0, right? So what this basically means is that all these vectors have unit magnitude and are orthogonal to one another, hence orthonormal. We can also generalize projection, right? Very similar looking formula to the one that you may have learned in high school. One thing to note here, though, is because this inner product is conjugate symmetric, the order of the terms in the numerator here does actually matter, right? This is not equal to inner product of xy. It has to specifically be yx. That's the definition. So I don't know, the way that I remember it is it goes yxy, right? Like that, the vector being projected is kind of being hugged in that formula there. It's in the middle. And just as we learnt for the regular dot product, we do have this nice result that a vector minus its projection onto another vector is always perpendicular to that second vector. So that should make sense. This is our y, and this is our x. Then this is the projection of x onto y, and this is x minus its projection. And you can see how that has to be perpendicular. Obviously, this is in a two-dimensional case, but it generalizes to even weird inner product spaces like function spaces. So we come to something called the Gram-Schmidt process. What we know is that every finite dimensional inner product space has an orthonormal basis. So given any basis, we can find an orthonormal one using the Gram-Schmidt process. So the intuition behind this is that if you have some sort of set of vectors, you can start with the first of them, v1, right? And say you want to add on your second vector, v2, but you want it to be perpendicular to v1. Well, what you can do is subtract from v2 its projection onto v1, right? And you end up with this vector. Now, it's a bit of a janky line, but you can see how that would be perpendicular to v1. And the key idea is that you can keep repeating this process, right? You can add another vector. So say we're in 3 dimensions and I add another vector that's kind of off that span. You can project this third vector onto this orthogonal set that you've already created, right? So you can project it onto v1 and project it onto v2 and subtract those projections from v3, and maybe end up with a vector that goes out like this somehow. And you'll end up with one that's perpendicular to both w1 and v1, right? And you can keep repeating this process up to whatever dimension your vector space is. So to formalize it, this is what the process actually looks like. Given any basis, v1 to vn, we can construct an orthogonal basis, W1 to Wn, where for each Vk, so let's look at V2 for instance, Wk is equal to Vk minus its projection onto all the W's before it. So say in the example of V1, W1 is V1 minus the projection of all the W's before it. Well, there are no W's before W1, so you don't have to subtract anything. As for V2, you need to subtract its projection onto all the W's that came before, in which case, which in this case is just W1, right? And for V3, you need to subtract its projection onto all the W's that came before, which is W1 and W2, right? And that's why we subtract two things. And you repeat this up until Wn. Of course, we want an orthonormal basis, not just an orthogonal one. So for each of these W's, we're going to have to rescale them. So our first basis vector will be W1 over its magnitude. And obviously we repeat that all the way up to En, which will be Wn over magnitude Vn. That makes sense so far? All right, so let's do an example. Here we have two vectors, and the question says to find an orthonormal basis for the span of V1, and V2, which is orthonormal with respect to the inner standard product, standard inner product on C3. So the fact that we're asked to produce a orthonormal basis for a given span in this question should already tell us that we're expected to use Gram-Schmidt. So let's give that a go. Let's start with W1. It's equal to V1 minus its projection on all the W's that we've already calculated, which is none. So it's just equal to V1. And for V2, W2, it's equal to V2 minus its projection onto W1. So let's calculate this projection separately. We know from the formula that this has to be W1 V2 over inner product of W1 W1 W1. And using the matrix notation that we learned before, matrix multiplication notation, we are going to rewrite this as I0 conjugate multiplied with I26, and then again 1I0 conjugate multiplied by 1I0, or multiplied by 1I0. Right, so I'm just substituting in the vectors. And that should yield I minus 2I plus 0 at the top. So minus I. And then at the bottom, it's just going to be 2 multiplied by 1I0, which is equal to what am I saying? 1 on 2 minus I 1 0. Right? So that's the projection that we need to subtract from V2. So we'll just fill this in here. We know that W1 is going to be 1I0. And we know that W2 is going to be I26 minus 1/2 what was it? Minus I10, which is going to equal, what's that going to equal? 3 on 2i, 3 on 2, 6. Right? And then finally, we can rescale these vectors to get an orthonormal basis. So E1 is going to equal W1 on the magnitude of W1, which ends up being 1 on root 2, 1i0. And E2 is going to end up being W2 on the magnitude of W2, which I'm just going to skip the computation here. I think it's going to be, well, 1 on 3 root 2, I14. So these are the two basis, orthonormal basis vectors that we've produced. So we can say that this new basis, E1, E2, is an ortho basis for span V1, V2. And that's question done. Cool. And just one thing to note here. On an inner product space, the magnitude of a vector is defined as the square root of the inner product of that vector with itself, right? This should look familiar because this is, on the vector space of vectors with real components, on Rn, this would just be W1 dot W1, right? Which is just the magnitude squared of the vector. Okay. And I do believe, yeah, we get the same result here. Cool. So a new concept that we're introducing is the orthogonal complement, right? This is defined in terms of a given subspace W of a vector space V, right? So this symbol, right, W raised to the power of a perpendicular looking symbol, which you can pronounce as W perp, or at least that's how I pronounce it, is the orthogonal complement of a subspace W. And it's the space of all vectors in V which are orthogonal to every vector in W. So if you were to write this in set notation, W perp is equal to the set of vectors in V such that the inner product of X with lowercase w is equal to 0 for all W in your subspace W, right? And this turns out to be a useful concept because for any finite dimensional vector space V and a subspace W of V, we have that W, the direct sum of W and its orthogonal complement, W perp, is V, right? So you can think of it for any subspace W, W perp is like all the space that's left over, right? Or another way to think about it is the span of all the basis vectors that are left over, right? This means that any vector X in a finite dimensional vector space V can be expressed uniquely as a sum of a vector from W and a vector from W perp, right? So just to visualize this with an example, right? If we're in R3, our subspace W could, for instance, be a plane. Whoa. Right? Oh, bit of a janky plane. You get the idea. It's a plane, right? And necessarily the orthogonal complement to that subspace, right? The set of vectors that are perpendicular to everything in this subspace is the span of the normal vector of that plane, right? And you can see how any given vector in R3 now, right, is you're going to be able to express it as a sum of some vector in W perp and some vector in W, right? So the same logic applies to any finite dimensional vector space V and any subspace W. And now that we are familiar with the concept of, decomposing using the subspace and its orthogonal complement, we can define orthogonal projections, right? So we define this vector A, this unique vector A, to be the projection of X onto the subspace W, and the vector B as the projection of X onto the orthogonal complement of that subspace, W perp. Notice that this definition does not actually tell you at all how to compute these projections, but we will get to that in a bit. And just as with, or at least a similar result to the one that we saw earlier, X minus its projection onto W is going to result in a vector that's in the orthogonal complement in W perp. So here's an example. We have W as a span of two vectors in R4. And we're asked to find the projection of this vector X onto W using the usual dot product on R4. So what do we start with? We can first recall that X is going to be equal to A plus B, where A is in W and B is in W perp. So, and we're given that this space W is the span of these two vectors, which are not dependent. They're linearly independent, so we can treat them as a basis for W, and we write A as a sum of V1 and V2, right? And that means that X minus lambda 1 V1 minus lambda 2 V2 is going to be equal to B, which is in W perp, right? Which by definition means whatever we have on the left-hand side here is going to be perpendicular to anything in W, right? So the natural choice of what to take the inner product with is going to be V1 and V2, right? So now we know that X minus lambda 1 V1 minus lambda 2 V2 inner product with V1 is equal to 0, and X minus same thing all over again, V2 inner product with V2 is equal to 0, 2. So if we actually plug in our known values for these vectors, we're going to get that the inner product of X, which is 1, 0, 0, 1, 0, 0, 0. Actually, we'll just bring it through straight away. Recall that this real dot product is linear in the second argument too. So we can just expand this out like this. Times v1, which is 1 minus 1 minus 1, 1 minus 1 minus 1, 1, minus lambda 1 minus 1 minus 1, 1, dot product 1 minus 1 minus 1, 1, minus lambda 2. This one is 1101, 1101, dot product 1 minus 1 minus 1, 1. And this all should equal to 0. And the second line is something very similar, except we have 1101 here, 1101 here, 1101 here, also equals to 0. So simplifying this, we're going to get 1 here minus 4 lambda 1 minus, what is it going to be? 3? No. Is it 2? 1 minus 1 plus 1. Oh no, it's just 1. Minus lambda 2 is equal to 0. And here we're going to get also 1 minus lambda 1 minus 3 lambda 2 is equal to 0. So we can solve this simultaneously. We now know that this implies that 1 minus lambda 1 minus 3, I'm just going to substitute in from equation 1 here. 1 minus 4 lambda 1 is equal to 0, which implies that minus 2 minus 1 plus 11 plus 12 plus 11 lambda 1, is that right? Is equal to 0. So lambda 1 is equal to 2 on 11. And we also get that lambda 2 is, I think, 3 on 11. So just some linear equations there to get to solve for lambda 1 and lambda 2, which are our expression, which is our coefficients of v1 and v2 in our expression for a. So now we know that a is equal to, which as we know is by definition equal to the projection onto W of x, is equal to 2 on 11 times v1, 1 minus 1 minus 1, 1, plus 3 on 11 times v2, which is 1101. And this is going to equal 1 on 11, 5, 1, minus 2, 5, I think. I hope. And that's our answer. That's the projection of x onto W, right? So this kind of method should be pretty easily replicated for whatever form of question you get like this. If in the special case where the span that you get, where the set of vectors that you're projecting onto is orthogonal, then your projection will actually be the sum of the vector's projection onto each of those vectors. I hope that makes sense. Like if your W is a set of v1, vn, where this is span, if your W is a span of a set of vectors where this set is orthonormal or even orthogonal, then the projection, projection of a vector x onto W would just be equal to the sum of its projections onto the vectors that you're given, because they're orthogonal. I hope that makes sense. That's just a special case where it becomes easier. But in general, you're going to have to be doing calculations like these. And we do get the same result. Lovely. But you can actually perform a shortcut for these computations using matrices, right? So the reasons for why this formula works will be explained a bit later. But if you construct a matrix A of the basis vectors of W, right? So if you construct A to be the matrix V1, V2, all the way to Vn, then you can actually apply this theorem and compute the projection of X onto W directly. Oh, wait, no, sorry, the projection of a vector B onto W directly. You just need to apply this monstrous matrix multiplication on the left. And I'm not going to compute it here, but you can see that once you crunch through all of this algebra, you do get the same result at the end. And this star is the adjoint. It's an operator on linear transformations and matrices, which we're going to go into soon. But first, QR factorization. So the theorem is that if we have a full rank P times Q matrix A, so all its columns are linearly dependent, that's what it means, we can factorize it into the product of two matrices, Q and R, where Q is a P by Q orthogonal matrix and R is an invertible Q times Q upper triangular matrix. So just to visualize that for you, Q is going to be have columns that look like this, right? Wait, no, sorry. Is going to have Q columns, sorry. And R is going to look something like this, right? So, you know, lambda 1, 1, lambda 1, 2, the 2, 2, right? And all of these entries underneath are going to be 0, because it's upper triangle, right? So where does this come from? How are we doing for time? Pretty badly. This comes from basically the computation that you perform when you do Gram-Schmidt. Gram-Schmidt process actually hands this factorization to you, as you'll see here. So this is actually your expression for what Q and R are going to look like in your QR factorization. We've got these columns, Q, which we're regarding as vectors, and the entries along the diagonal of the upper triangular matrix are the magnitudes of W's, which you recognize as the values that are generated in the Gram-Schmidt process, right? So in order to perform a QR factorization, the idea is that you perform the Gram-Schmidt process on the columns of A, right? And we're going to see this in action shortly. Yeah, see? So what it says here is that WK are the vectors found directly by using the Gram-Schmidt process on the columns of A, right? And these A vectors are precisely what we mean by columns of A. Yeah. And the Q columns are the normalized vectors that we find through the Gram-Schmidt process. So let's do an example here. As you can see, you don't have to perform factorization on a square matrix. It can be anything. So let's do it on this one. So our first step is going to be to perform the Gram-Schmidt process on the two columns that we've been given. So W1 is equal to V1 is equal to 1, 1, 1, 1. And W2 is equal to V2 minus the projection of V2 on W1, which, just to spare you the algebra, is going to be equal to 1, 1, 1, 1 minus 4 on 4 minus 1, 0, 2, 3. No, sorry. So V2 minus 1, 0, 2, 3 minus 4 on 4 multiplied by W1, which is 1, 1, 1, 1, which yields minus 2, 1, 1, 2. No, wait, sorry, minus 1 here. So our Q1, we're using Q's instead of E's here, but it's essentially the same process. W1 over magnitude of W1, which is going to be 1/2, 1, 1, 1, 1. Q2 is going to be W2 on the magnitude of W2, which is going to be equal to 4 plus 2 plus 4. What is that, 10? 1 on root 10 times minus 2 minus 1, 1, 2. So we found the columns of our Q matrix, right? Just Q1, Q2. And to find our R matrix, we know that it's going to be a 2 by 2 matrix, right? Because B has 2 columns. It's going to be a 2 by 2 matrix. Diagonals are going to be lined with the magnitudes of our W's. So W1, W2. This entry is going to be a 0. And this entry here is going to be one of our Q vectors multiplied with a column of A. Specifically, is going to be the first Q vector multiplied with the second column of A. And this matches our theorem here, right? So the numbers that you use here are going to be equal to the row followed by the column, right? So here, in this case, you can see that this entry is in the first row and the second column, so you have 1 and 2. And in this case too, we have the first row and the second column. So we're going to be computing Q1 multiplied by Q2. So we can fill that in pretty easily. W1 is just 2. The magnitude of W1 is just 2. The magnitude of W2 is root 10. We keep the 0. And then the inner product of Q1 and A2 is equal to Sorry, hold on. Hello?
I was checking the confirmation that like in the action chat.
Wait, hold on. I'm still presenting. All good. I don't want to keep you guys here, by the way. I know we're going a lot over time. You're free to leave. I'm still like streaming to the YouTube and it's recording. So yeah. Huh? Yeah, it will be on the channel. Yeah, that's all good. So the inner product of Q1 and A2 is going to be, we're going to write it in the matrix form again. What's Q1 here? 1 half 1 1 1 1 multiplied with A2, which is minus 2 minus 1 1 2. Minus 2 minus 1 1 2. And that's going to work out to be something not quite right. Q2 and A2. Seems like it's just going to be 0, right? Is that right? I don't think it's supposed to be 0. I think I made an algebra mistake somewhere.
That's yeah.
0 here?
Yeah.
Minus 2, minus 1, plus 1, plus 2.
Shoot.
So it should be 0.
Yeah.
Okay. I'm pretty sure this. Okay. Maybe my memory fails me. Anyway, so we get the gist here. We've got our R matrix, and then we can conclude by saying that A equals QR, right? So we found our factorization. But something clever that you can actually do to find this R matrix instead, especially for when you have a higher dimension, is given that you know that A is going to be equal to QR and Q is an orthogonal matrix, you can multiply by the adjoint here, which we're going to go into in a bit, which is going to cancel out with Q, right, as one of the properties, and we're just going to be left with R on the right-hand side. So multiplying Q adjoint by A is also going to yield R.
That's how I usually remember. R equals QT. Okay.
And that should actually yield the same result. So let's check if I indeed did make an algebra mistake somewhere. What? Q1, A2 is supposed to be 2. How did I mess up? Q1 times A2 I'm not sure what I did wrong there. But in any case, the method is clear. And that's how you would find it, either by filling in the entries manually or by performing a computation like this. All right, let's move on. So now actually onto the adjoint that we've mentioned multiple times already. So the adjoint is an operator that you can apply to a linear map, defined as follows. For any linear map T from a vector space V to a vector space W, there is unique linear map T adjoint where that maps from W to V, where the inner product of any W with T of V is always going to be equal to the inner product of T adjoint of W and V, right? So what this essentially means is that the adjoint is an operator that allows you to kind of swap a linear map between the two sides of an inner product, right? The only thing you have to do is apply the adjoint to it. So here are some properties of them. They preserve addition, multiplying by a scalar on the inside is equivalent to multiplying by the conjugate of that scalar on the outside. It inverts itself, so the adjoint of the adjoint is just the original map, and it flips, right? In the same way that a transpose reverse the order of two matrices, right? So AB transpose is equal to B transpose A transpose. The adjoint does something similar, right? So the adjoint of U compose T is the same as T adjoint compose U adjoint. So in the context of matrices, right, if we have T as a linear map, then the adjoint map of T, the adjoint of T, is simply the conjugate transpose of T. So what this means is that if you have that this transformation T is defined through a matrix multiplication, then the adjoint map is going to be equal to the transformation defined by the conjugate transpose of that matrix, right? And for this reason, we also write just as shorthand that A star, where A is a matrix, is the conjugate transpose of that matrix, right? That's how we were using A star before, if you recall. So let's see what's happening here. We are actually asked to find an expression for the adjoint of a linear map here. This is quite a unique question. So the first thing they ask us to do is to find an expression for this inner product, right? So we're asked to find the inner product of P0 plus P1T, which is an element of the vector space of first degree polynomials in T, and T of X. Oh, yeah, T of X, where X is this vector, X1, X2, and we are given the definition of the inner product on this space, right? So it's a bit of a funny one. We haven't seen this before, but we can compute it. So this is going to equal inner product of P0 plus P1T with the transformation of X through T, which we're given here as well. It's X1 plus 3X2 plus, what is it? 2X1 minus X2T. And applying this inner product definition to our inner product, we're going to have the constant term on the left multiplied by the constant term on the right, P0 times x1 plus 3x2 plus, you can see how this is just the coefficient of t on the left multiplied by the coefficient of t on the right. So P1 times 2x1 minus x2. And we want to define this, right? Because we're looking for the adjoint, we want to change this into a form where it's a inner product in the world of x, right? Which is R2. So we want to rearrange this to be some linear combination of x1 and x2. And what that's going to be is x1 multiplied by p0 plus 2p1 plus x2 multiplied by 3p0 minus p1. Which is equal to the inner product now in R2 of x1, x2, and p0 plus 2p1, and 3p0 minus p1. Right? We're just rewriting this in a form using the real dot product, right? And so we have that. We can rewrite this as x1, x2, and a transformation, say g of p0 plus p1t, where g is equal to g of p0 plus p1t is equal to p0 plus 2p1 3p0 minus p1. So we've basically rewritten this inner product in a form where the transformation is now not applied to x, but applied to the polynomial term, right? So we basically moved this transformation t from one side to the other. And we know that this expression that we've found is going to hold for any x1, x2, any p0, p1. So it must be that g is equal to t star, right? So that's our expression for t star.
So that's going to be 2601 content.
Hmm?
Is the rest of the slides going to be 2601?
There's later stuff on method of least squares that we can cover briefly.
Because I do 251.
Yeah. So for you, I guess you would, there's this formula basically, and also parts on determinants. But I think that's all. I'm not sure how much of that is 2501. Brendan, do you recall? Does 2501 do any determinants?
Certainly they do. We did determinants.
Are you learning the other forms of the determinants?
Like the minor major expansion.
Yeah, stuff like that. Or the what's it called? Is this Leibniz form?
I don't know what that is.
No? Okay.
I've seen with Bob that.
Yeah, okay.
Simon.
Yeah, I mean, we're still going to be doing a bit of 2601 stuff. If you want, you can just watch over the relevant parts in the recording later on, once it's uploaded.
Okay.
But yeah, up to you.
Thanks.
Okay. And yeah, we do yield the same expression. Wait, except there's a plus instead of a minus here. Where are we? X minus 2 minus x2. I'm not sure why that's a plus or not, and not a minus, but you can see how it looks similar in the very least, right? Okay, now types of maps. We've already touched on this a little bit with when we talked about orthogonal matrices and their properties. Here, we kind of generalize that to linear maps in general. We have these new concepts of unitary and Hermitian linear maps. So a unitary map is a map for which its adjoint is equal to its inverse, right? So just to provide some intuition for what these maps look like, in R3, these are reflections and rotations, right? So whatever they are in other vector spaces and in other dimensions is just a kind of a generalization of that. Hermitian is are linear maps for which their adjoint is equal to themselves, also called self-adjoint. And an isometry is a linear map for which is a linear map that preserves distances, basically, right? Preserves the magnitude of the vectors. So yeah, just a reminder here, the adjoint of a matrix is referring to its conjugate transpose. And we do have a theorem that a linear map is an isometry if and only if it is unitary. So a linear map is called unitary if and only if it is distance preserving, right? Which is interesting to think about. It gives you a better idea of what these unitary maps really are. So we've got an example map here, right? T of WZ is TZ minus W, defined with the standard inner product, right? Is T isometric and is T Hermitian? So we can define T of WZ to be some matrix multiplied by WZ, where A is a 2 by 2 complex valued matrix. Then we have that A of WZ is equal to 0 times W plus 2Z in the top, and minus 1 times W plus 0Z in the bottom, which is equal to 0, 2, minus 1, 0 times WZ. So we have an expression for our matrix A. So we have that A is equal to 0, 2, minus 1, 0. A star, which is the conjugate transpose, is going to be just the transpose of this matrix. Minus 1, 2, 0. And the inverse is going to be 1 over the determinant, which is 1 over 2, times 0, 0, minus 2, 1. And from this we can see that A does not equal A star, so it's not Hermitian. And A star does not equal the inverse of A, so it's not unitary, which implies that it's not isometric. All done. All right, now going into the last kind of part of this section, the method of least squares. So basically, this is kind of a generalization of our process of solving linear systems, right? So as you may know, this system AX equals B is not always solvable. In the sense that trying to solve it would actually yield a contradiction, right? So there's no solution to this system. So we kind of generalize this to a method that seeks the X for which AX is closest to B, right? And this is actually always solvable, right? You will always be able to find such X, right? Or if not a unique X, then the subspace of vectors which minimize that distance between AX and B, right? And this method is quite simple. You solve this modified equation, this equation where both sides were multiplied on the left by the adjoint of A. For Math2601 students, you're not going to have to consider any complex matrices in this part of the course, so this is equivalent to just multiplying on the left by the transpose of that matrix. And let's give it a go, right? Oh, and of course, if A has independent columns, right, then this matrix A star A is invertible, right? So we can multiply by the inverse of A star A on the left of both sides of the equation and isolate X, in which case we get this expression for this solution that minimizes distance between AX and B, right? This method is called the method of least squares because in a way you're minimizing the distance squared between AX and B. So let's give this one a go. We've got that we're finding our solution is our equation for which we want to find the closest solution is mx equaling y. So what we do is we multiply on both sides by the adjoint of m. So we are solving adjoint mx equaling m adjoint y. So first, let's find m adjoint m. It's going to be equal to, because we have a real matrix here, is just going to be equal to the transpose. There are no conjugates required. 2, 2, 3, minus 1, 2, minus 1, 4, 2. Multiplied by just the regular m, 2, 2, 3, minus 1, 2, minus 1, 4, 2. Equal to, that first one is 4 plus 9 plus 1, which is 18. 4 minus 2 is 2, plus 12 is 14, minus 2 is 12. This is going to be 12, 2. And at the bottom, we have 4 plus 1. 4 plus 1 plus 16. So 21 plus 4. 25. And this is a symmetric positive definite matrix. Oh, sorry. Well, it's a symmetric matrix. So we can attempt to invert it. The inverse here is going to be equal to 1 over the determinant, which is going to be some large number. If you give me a second. $18 times 25 minus 144 is 1 on 306, multiplied by these entries switched, minus 12, minus 12. And that's the inverse. Oh, sorry. I don't know why I equated those two. This implies that the inverse of m star m is whatever we calculated here. M star m inverse is whatever we calculated here. So our solution x is going to be 1 on 306, 25 minus 12 minus 12, 18 times m star, right? I'm just following the expression that we have here. So times m star, which is 223 minus 1. 223 minus 1, 2 minus 1, 4, 2. Right? All multiplied by the vector that we get, y, which is 1, 2 minus 2, 6. Right? I'm not going to crunch through this algebra, but in any case, you can see where you would go from here. The main idea is to actually leverage this adjoint to find the solution, to find the closest solution to this linear system. Yep, and we get something that looks similar, right? Okay, finally onto the next topic, determinants, the last topic for this seminar, which we'll have to speed through. We start with the definition of a permutation, right? A more rigorous definition than we heard before. We now define it as a bijection from a set to itself. So if we have some function that maps, say, the set of integers from 1 through to 4 to itself, right, somehow like this, then we can treat that function as the permutation, right? And we have this new notation for this permutation, which is denoted through the symbol sigma, right? So one fact that ties into what we learned previously is that the permutations of a set of n elements forms a group called the symmetric group under composition. For instance, S3 is the group of permutations on the set 1, 2, 3. We also represent the kth element of the permutation as sigma k. So when we permute two elements, i.e. swap them, we call this an inversion, right? We now define a function called the sign of the permutation, right? Which is essentially the number of inversions you need to perform which is defined through the number of inversions you need to perform to reach that permutation, right? It's, like it says here, an indication of how many inversions it creates. If there are an even number of inversions, the sign is 1, and sigma is said to be an even permutation, right? Otherwise, the sign is -1, and sigma is said to be an odd permutation. So here we have an example here. We have to find the sign of this permutation, right? The permutation that rearranges 1, 2, 3, 4, 5 to look like this, 1, 3, 2, 4, 5. Well, you can clearly see that the only thing that happened here was one swap. So the sign of the permutation would be 1, would be -1, right? So the way we'd write that is sign of sigma is -1, right? And identify sigma 2, that's just the second element of the permutation, that's 3. Very quickly, I'll give you guys a very clever way to count these, to count the sign of a permutation or the number of inversions it creates. If we start with some set, say the integers from 1 through to 4, and we have some permutation, say 4, 2, 1, 3, right? Something we can do is join all the corresponding elements of these permutations, right? And if we count the number of crossings that our lines make, then that'll actually be the number of inversions, right? And we can verify this by looking at all the pairs of elements in this permutation and counting how many of them are out of order. So we start with 4, 2, then 4, 1, 4, 3, then 2, 1, 2, 3, and 1, 3, right? So 6 pairs altogether, as expected. And how many of them are out of order? 1, 2, 3, 4, right? 4 pairs of out of order. That also means that this permutation is of 4 inversions, right? And of course, that means that the sign would be 1. So, 2 ways to count the inversions of a permutation. We proceed. Properties of the sign. It's a group homomorphism. So composition inside is the same as multiplication outside. The sign of a transposition is -1. That means that swapping 2 elements, right, is the sign of that permutation is -1. That makes sense because that's just one one inversion, sorry. And thirdly, every permutation can be expressed as a composition of transpositions. The sign of a permutation is -1 to the k, where k is the number of transpositions required to make that permutation. So that should hopefully make sense, right? Given any permutation, you can reach that permutation by combining a bunch of swaps of pairs of elements, right? And the sign, as described before, is just -1 to the power of that number of -1 to the power of the number of inversions or the number of swaps required. Now we can use this new definition of the sign of a permutation to define the determinant, right? The determinant is the sum across every permutation of p elements, right? Given that we have, given that the matrix is a p by p matrix, of the sign of the permutation multiplied by the product of the elements of the column corresponding to that permutation. So maybe to visualize this, right? A, B, C, D, E, F, H, I, J. For each term in this sum, you're going to be permuting. You're going to be choosing a permutation first of all, right? So 1, 2, 3. Maybe our permutation is 2, 1, 3, right? So we're going to choose the second element of the first column. Or rather, I guess according to this definition on the right, it's going to be the element in the first row. First row and second column. First row and second column. Second column, first row, and third row, third column. Sorry, I think I misspoke there. What I meant was first row, second column, second row, first column, and then third row, third column, right? We take the product of these elements. Oh, whoops. Take the product of these elements, B, D, E, right? And we multiply it by the sign of our permutation, where this is our permutation, right? And that's how we get one term of this sum. But we're going to be doing that across every permutation possible, right? Of course, this is not a very nice way to actually compute the determinant. We have another theorem, which is proven through the theorem above, or the definition above, which is basically a generalization of the method of expanding along a row, right? So if you have a matrix, if you have a matrix, and you have, say, a column here, right? So A1, A2, I guess it would be A1J, A2J, A up to PJ, right? You can expand along that column or row, right? Equivalently, by taking a sum of for each element in that column, right? -1 times I plus j times the actual element that you're considering, so 1j in this case, and the determinant, a smaller determinant of the smaller matrix formed when you exclude all the elements of the matrix that are in line with A1j, right? So all of these ones, you'd be excluding all of these, right? And you're left with another square matrix formed by like pushing the remainder together, right? This new matrix formed by excluding one row and one column is called the minor of the matrix, the IJ minor. And this kind of forms the basis of that method of expanding along a column. Hopefully that makes sense. Okay, finally some properties of determinants. So first three properties: the determinant of an upper triangular or lower triangular matrix is simply the product of the diagonal terms. We should know that from first year. The determinant of a matrix is equal to the determinant of its transpose. The determinant of a matrix is equal to the conjugate of the determinant of its adjoint. Some more properties. If a permutation is applied to the rows of A, the determinant is multiplied by the sign of the permutation, right? That's because you can just think of that permutation as repeatedly applying different swaps. And as you know, swapping the rows of a matrix multiplies this determinant by -1. Next, the fifth property: if any row of A has a multiple of another row added to it, the determinant is unchanged, right? That's one of the elementary row operations. If a row of A is multiplied by a constant alpha, the determinant is also multiplied by alpha. Any matrix with a 0 row or 0 column has a 0 determinant. All of these should be pretty familiar. So finally, a question to do with determinants. We're asked to prove that the determinant of this matrix A is equal to some multiple of the determinant of this matrix B. So let's start with this left-hand side, right? A plus B plus C. Determinant of B. We know that multiplying the determinant is the same as taking the determinant of a new matrix where a row or column has been multiplied by that factor. So we can see in B, there's a row that's conveniently all ones, which would be very easy to multiply by A plus B plus C. So let's see where that gets us. Determinant of A plus B plus C, A plus B plus C, A plus B plus C. We've got 2B, 2C, 2C, 2B, and here we've got B minus C minus A, and C minus B minus A. Okay, and we know that this is supposed to be equal to the determinant of A. So we want to make that matrix look like this matrix, right? Well, we know that applying elementary row operations, specifically adding a multiple of one row to another row, does not change the determinant. So we can fiddle around with that and see where that gets us, right? Specifically, we could try looking at that first column and noticing that A plus B plus C minus 2B minus 2C is going to get us exactly the term that we want to be there, A minus B minus C. And once we notice that, we'll see that the same applies for all of these terms as well. So actually what we want to do is convert this to this matrix, A plus B plus C. Wait, yeah, we could just rewrite it as A minus B minus C. This is going to be minus 2C, and it's going to yield 2A there. Yep, 2A there. 2A is going to be here as well. A minus B minus C, A minus B minus C, 2B, 2C, 2B, 2C, which is equal to the determinant of A, because that matrix on the inside is A. And we can justify this equality that we've made by just demonstrating the elementary row operation that we've done. Right, so R1 is equal to R1 minus R2. R1 is equal to R1 minus R3, right? And that's all we need to do for this question. Moving on though, we want to now show that the determinant of B is equal to the determinant of this new matrix, right? Well, we can apply the same property, right? We know that the determinant of B is equal to 1, 1, 1. B2C, B minus C minus A, 2C, 2B, C minus B minus A. And yeah, right. So we can also apply that same operation of adding a multiple of one row or column to another row or column while keeping the determinant unchanged. Right, hold on, I'll write this down properly. So we can see that the matrix that we're trying to convert B into has that first column unchanged, right? But in this top row, the ones have become 0. So it looks very suspiciously like that first column has been subtracted from everything else. And indeed, if we do that, 1 to B to C, this 1 becomes a 0. This 2B becomes a minus B minus C minus A. This 2C becomes a 0. This 1 becomes a 0. This 2B becomes a 0. And this C minus B minus A becomes a minus C minus B minus A. Right? Which we can rewrite as the determinant of 1 to B to C, 0 minus A minus B minus C, 0 minus A minus B minus C, 0, 0 as required, right? So that's the Benton solution. And next we're asked to find the determinant of B, right? And to hence give a factored form of the determinant of A. So we have this much sparser form of the determinant of B, right? And we can notice that this is actually a lower triangular matrix, right? And from the properties above, we know that the determinant of this is just going to be the product of the terms on the diagonal, which is going to be minus A minus B minus C squared, which is equal to A plus B plus C squared. And so, from before, we know that the determinant of A is equal to A plus B plus C times the determinant of B, and hence this has to equal A plus B plus C all cubed. And that's the end of the question. That also brings us to the end of the seminar, finally, an hour over time. Thank you all for tuning in, or watching from home, or watching later, and best of luck in your exam. Do note, the next seminar is tomorrow in Patricia O'Shane, Geo6, and it's being run from 1 p.m. to 3 p.m. So it's right after that exam revision session that Sean is running. So you better be there. All right. Thanks for tuning in. And we need to end the stream. Oh boy.